So good afternoon, everyone, and welcome to the 2DCC webinar on bulk crystal growth of chalcogenides. Today we have Dr. David Snyder, who's the Department Head for Electronic Materials and Devices here at Penn State for the Applied Research Laboratory. Today he's going to be giving a talk a little bit about some bulk crystal growth research that is going on in 2DCC, as well as some opportunities that are coming up very soon. So just so you know, everyone online, that these presentations are recorded. At the end of the presentation, we'll accept questions online and be able to moderate those questions, and Dave will be answering them. So without further ado, David Snyder.
So good afternoon, everyone. I'm Dave Snyder. My current position is as the head of the Electronic Materials and Devices Department within the Penn State Applied Research Laboratory. It's a Navy University-affiliated research center here at Penn State. We also have adjunct positions in the Chemical Engineering Department and in the IGBP and NATSE. I've been with Penn State for 18 years, and I've been involved with crystal growth of thin films and bulk materials for longer than I care to admit, but about 30 years. So I'm very pleased to be here today to talk about the bulk growth initiative under the 2DCC. I'm very excited to be part of this initiative because I think this is a great opportunity to take advantage of this component of the 2DCC to enhance the overall effort. Today, what I'll be doing in terms of the presentation is giving you a very high-level overview of what we're doing here since we're really just getting started. The purpose today is to kind of introduce everyone to the bulk growth effort, get everyone thinking about what types of materials might be of interest, how these capabilities might be able to be used both in the internal and the external research programs. So I'll begin with just an overview of the scientific goals for the bulk effort. Spend a little bit of time talking about chalcogenide materials, why they're of interest. I think most people are familiar with this, but from the bulk perspective. And then the majority of the time today I'd like to spend really talking about what we're doing in terms of setting up bulk growth processes, equipment, and capabilities here under the 2DCC. This is not a major part of the effort, but it's an important part that we're just bringing online some capabilities. I think this is a good time to introduce this topic and begin to solicit research proposals. Then talk a little bit about some of the work that we have started, looking at transition metal dichalcogenides in terms of bulk growth and topological insulator materials. And then wrap up just by reiterating that there's currently a bulk growth request for information out there. We're looking for input from the community, both internally and externally, in terms of the bulk growth area, materials of interest, research objectives, information like that, anything you can provide. We're going to take this information and use it to generate a bulk growth research proposal solicitation, which we expect to be released next month. The key personnel in terms of bulk growth are shown here. Tom Baluk from chemistry, bulk synthesis and exfoliation. Myself in terms of bulk synthesis. Joan, platform director and synthesis lead. And Josh, director of user programs and CVD growth. We have 3 part-time staff involved with this. Randy Cavallero and Robert Laval are 2 engineering support specialists in my department. Randy's got an extensive background in bulk crystal growth, particularly Bridgman growth. Also, Ron Redwing is involved as a key component of the team here. And we're hoping to bring on a postdoc researcher and a research technologist to broaden out the team and the capabilities as this new equipment comes online. So again, just to take a minute and give a quick overview from the 2DCC platform and how bulk growth fits in. The 2 main components of the 2DCC are to develop custom deposition tools, in situ and real-time characterization of monolayer and few-layer films, and then look at unique capabilities in terms of simulation of reaction kinetics through first principles. 3 major components: synthesis task, in situ characterization, and theory and simulation. There have been previous webinars which have covered in detail the MBE, MOCVD, characterization, and theory components. So just encourage everyone, if you haven't seen those, to take a look. Today, what I'll be presenting on is giving an update on the bulk growth component of the synthesis task and trying to give you an overview of what we're doing and how it ties into these other components. The scientific goals of the bulk growth program are shown here. First of all, trying to develop capabilities to prepare high-quality bulk crystals for a wide range of chalcogenides. really be able to use this then to investigate equilibrium growth of alloys and dope crystals, which are of greatest interest in this material system, and then compare the materials that we grow in a bulk form to thin film materials, looking at how the properties differ depending on the growth conditions. We also want to use this capability to explore the synthesis of new materials, new compositions, new doping levels in these crystals in a well-controlled environment so that all the details of the growth are well known, well understood, and well documented, and be able to correlate this with subsequent work. We'd really like to try and see this tied into the other components of growth in terms of the epitaxial growth. And then finally, looking at this effort as a way of providing substrate materials to the community. Typically substrates for crystal growth, you want something that's very inert, doesn't participate, it's just a template to grow on. But there's a lot of interest now in active substrate materials for various applications. And so we want to be able to provide materials and substrates in a form with the right size, shape, surface finish, characterization, etc., to be used for subsequent growth. And in fact, we're actually actively encouraging collaborations where substrates and film growth can be combined in the scope of a larger program. Bottom line takeaway, the bulk growth effort will provide opportunities for 2D materials discovery as well as for benchmarking against other growth techniques. I just threw together a list of a bunch of different 2D chalcogenide materials, mainly to make the point that there's just a very wide range of materials out there. And I think this is one of the things that I find most exciting about this field. It's new, but it's got just a huge range of materials that you could look at, many with unique properties and many with unique growth challenges. So from a crystal grower's perspective, this is just a really exciting place to be in terms of trying to figure out how to grow these materials, control the properties, look at all the other factors that affect the growth, the quality, and then combining them in terms of doping and other structures and integration. So I guess it's just a really wide open and very exciting field. From our point of view, the materials that are of immediate interest from the bulk perspective are as shown here. We've started some work looking at chalcogenide topological insulators. So traditional materials like bismuth selenide, bismuth telluride, alloys of these, as well as exploring some opportunities to look at topological crystalline insulators, such as shown there. I think this is another area where you get into these quaternary compounds and other growth challenges in a pretty wide parameter space. And I think this is where we will have the capabilities to be well suited to address these needs. The second major area is transition metal dichalcogenides. And we plan to initially start by looking at the materials shown there, tungsten ditelluride, moly ditelluride, tungsten diselenide, moly diselenide, and niobium diselenide. It's kind of an initial class of materials that will set up and start to grow during the first phase of this effort, and then expand on into alloys and variations from there. There's a great interest here to look at transition metal monochalcogenide superconductors and magnetic doping for the bismuth and antimony-based chalcogenides. So we're trying to focus on 2D chalcogenides in a broad sense, but I've identified a series of materials that we'll be starting with as we spit up this capability. I like this graphic from Das et al. Because it really does show the wide range of methods that you can use to grow these transition metal dichalcogenides. Many of them, metal transformation, CVD, MBE, powder vaporization, are centered on thin film applications. And I think this just shows the wide range of approaches you can use. And there's often not a lot of attention paid to the bulk component. There is some interest in taking natural bulk crystals and doing exfoliation, which is how a lot of this started. But most of these other growth techniques have really become the prevalent way of looking at it. What we're trying to do here is develop the ability to make tailored synthetic bulk crystals. And what I mean by this are bulk crystals with unique properties in terms of composition, doping, structural quality, etc., that really address a need for other applications that you can't get in terms of just naturally occurring materials. And doing this by a variety of different growth techniques. So the majority of what I would like to talk about is really centered in this area: tailored synthetic bulk crystals, by chemical vapor transport, vertical bridgman processes. And that's going to be the real thrust of the initial 2DCC bulk growth effort. So I'm going to go through each of the processes that we're setting up. I'm sure many of you have background, so please bear with me. But if you don't, I just kind of wanted to give a quick overview of each of the processes. So the first effort that we're setting up here in the 2DCC will be a vertical bridgman crystal growth process. And basically what this process involves is a crystal growth system in which you set up an axial temperature gradient with a hot zone and a cold zone. Typically load a source material in an evacuated ampule, typically in an elemental form. You go through a compounding step typically. You can either do this kind of in situ or in a separate system. We're actually adding a rocking furnace that will be used for compounding materials, particularly where there's a high exothermic heat of reaction. Once you have the material in a compound form, heated above the melting point, allow it to equilibrate, and then translate it through this temperature gradient. So through the melting point region, which you often can establish in a furnace through the zone configuration, internal baffling, etc. So there's some engineering that goes into designing these to get the gradients right, maximize the gradient, optimize the gradient without creating excessive stresses in the material. So you translate it to directionally crystallize the material. There's a couple of ways you can do this too to start. Often, when you're looking at larger crystal growth efforts, you'll use a seed crystal, partially melt it back, and then solidify off of that to set the crystallographic orientation and assure monocrystalline growth. Or you can self-seed either with a tapered seed structure shown in this schematic, or with a constrictive region, a pinch region, so that you select a single grain and then grow that out to try and optimize the structure of the grain. And then upon the completion of the translation, when everything is below the melting point, you stop, equilibrate the furnace, try and set up a uniform temperature profile, typically do some sort of in situ annealing of the crystal, looking at trying to anneal out possibly interstitial vacancy defects, reducing stress in the crystal, etc. And then can be unloaded from there. And as I mentioned, the growth can be seeded or self-seeded. And the bottom line for crystal growth using bridgman technique is you have to be patient, because it takes often many days to grow crystals. A typical time for crystals of this size with these materials would be between 3 to 10 days. And I guess that really limits the number of runs you can do and the time that it takes to go through this process. So a key part of the equipment that's being set up at the 2DCC is a new vertical bridgman system for melt growth. The vendor for this system is Mellon, and there's a couple of schematics of the system shown here. So this has been designed and specified to be able to do relatively large areas. So we can go up to 50 millimeter diameter, and we can configure this to go down to smaller sizes, down to 5 millimeter diameter crystals. So it gives us a wide range of flexibility in terms of the size. It's a typical conventional 3-zone furnace, and the maximum temperature of this system is limited to 1250 C. Most of the materials we're interested in, most of the growth processes are going to be done in quartz ampules, and so 1250 C is reaching the limit of the quartz. There are some materials of interest that go to higher temperatures where you have to use other materials such as platinum, iridium, etc. But this particular system, which is going to be one of the key pieces of equipment in the bulk growth, will be set up to focus on growth up to 1250. It will have functionality including crucible rotation, complete linear translation control, and data logging. The idea of being able to give you exactly the detailed information during the growth and consistently and repeatably grow these. Picture on the left shows kind of a photo of a similar type of system. So this system has been designed, spec ordered, and expected to be delivered next month. We think it'll be fairly quick to get this up and running given the experience we have. So hopefully if the delivery is on time in March, by May of this year, we expect to be in position to start to use this system for research projects. Beyond that system, there's a variety of other crystal growth capabilities here at Penn State. I have a laboratory in Innovation Park and in Freeport, Pennsylvania, with a variety of systems that are being made available on a limited basis for crystal growth programs in support of the 2DCC. So this slide just shows some of the other systems in my lab. We've got 3 of these new vertical bridgman systems that are slightly larger, 4-zone configuration. And a key feature here is we got higher temperature capability. So if someone really needs to look at a material, the melting point above 1250, these systems could be used for that. And again, they're fully automated, data logging, process control. So they're very well suited. Primarily, we're using these for lead-based piezoelectric crystal growth at the moment. And again, the high temperature capability is what's most interest. In addition, there are two other high temperature systems, which I'm calling large diameter high temperature vertical bridgman systems. And these are the systems that were currently used to start the growth of the topological insulator materials. These are 4-zone configurations. They've got 75 millimeter diameter capability, again, fully automated. And one of the things we've done in these furnaces over the years is use them to grow multi-boule runs. What I mean by that is instead of just growing a single boule, you make an array of boules. And you can do this if there's a fairly narrow temperature range which they solidify over. But it's ideally suited for looking at things like doping studies, compositional studies, where there's only a slight difference in the melting point. What this really does is allow you to quickly look at parametric studies over a wide range of composition or doping in these materials and get samples in a single run. And so this is what we've implemented for a variety of materials over the years. And this furnace has been configured to be able to do that. So, photo just shows a little better example of that. This furnace loads from the bottom, translates up into the hot zone, and then comes down through for the growth. And you see here there are 3 ampules that were produced in Tom Maluch's lab, ready for compounding, bismuth telluride with varying composition. And so we can do either single, 3, or 6 in the way that this furnace is configured. Lets you do a wider range of exploration in a single run to quickly generate samples. And so that pair of furnaces, I think, will be ideally suited for these types of studies if you have a case where you really want to do a wide composition or doping study. So the second area then, in terms of the 2DCC for equipment that's being installed and developed, process being developed for, is chemical vapor transport. If you're not familiar with this process, the basic idea is you use a transport agent to transport material from a source to the crystal. So you start by putting a polycrystalline sample and a transport agent in a sealed ampule, typically a quartz ampule. When you heat this up, the transport agent reacts with the source material, forms a gaseous species. And there's a hot section and a cold section. The material is transported down this temperature gradient, depending on if it's an exothermic or endothermic reaction. Typically, most of these are endothermic. You redeposit the material on the cold end and then release the transport agent and set up a circular cycle here for transporting material. There are 2 systems for chemical vapor transport that are going to be installed. One is ordered and on its way, should be here within a week or so. Another one that will be specified after that. So there'll be a fair amount of capability and capacity for doing this. And in conjunction with this, there's an ampule loading system that's being set up at the Millennium Science Complex that should allow for a wide range of transport agents, including iodine, bromine, chlorine, possibly some other materials. The takeaway from this process, it's a very good method for growing high-quality crystals, but it tends to be limited by the transport rate and growth rate. So, for doing research samples, this is a good way to generate material. When we decided to specify this, we decided to go with a 4-zone furnace. Typically, you often use a 2-zone furnace. This furnace will have 4 zones to allow for complete control of the axial gradient between the hot and cold sections, both in terms of the temperature differential and the gradient. We're hoping to be able to use this to manage the transport of the materials in an efficient way. This furnace is designed to be able to operate up to 1100 C, up to 2-inch diameter, fully automated. And we expect the first system to be delivered in March, available in about probably six to 8 weeks. The second system expected in June. So there'll be a capability coming online through the 2DCC for CVT growth of various materials. Another process which is of interest for some of these materials is physical vapor transport. In this process, what you're doing basically is setting up a temperature gradient between a hot and cold zone using a source material and transporting it, but you don't use a transport agent. For some materials, this process has advantages, particularly in cases where you're concerned about the transport agent affecting the property of the material. So this is just basically a vacuum, sublimation, condensation type of process where material is transported under vacuum down a temperature gradient. It's another process of interest for a variety of these materials. We've used this in the past extensively for 2,6 compounds as well as for materials such as silicon carbide. And there's currently 4 of these systems available for use depending on the materials of interest in support of the 2DCC on a limited basis. So we got a wide temperature range, a wide range of axial gradients. You can control transport in the furnace by the susceptor shape, because these are induction heated furnaces, the susceptor material, the coil position, and radiation windows. And so you have a very wide range of flexibility in terms of the transport. These are large systems that can be configured to be large systems up to 100 millimeter diameter, 200 millimeter length. And a key point with this is it's capable of very high temperature growth, get to 2,500 degrees C in these systems with the right design quite easily. And turbo pumps, so they're very clean, very high purity, fully automated. And I said we've used these in the past to grow a variety of materials. So I just put this slide in here just to make people aware, if there's a class of material where you think that this type of process would be advantageous over CVT, for example, it would be available. Another quick point in this, although graphene is not directly part of the MIP, we have here at Penn State the capability of doing large area sublimation growth of graphene, and a lot of work was done by Josh Robinson early in this program to develop processes to synthesize hydrogenate epitaxial graphene and CVD graphene up to 100 millimeter diameter samples. And if these are of interest, by combining them with other material systems, this capability is available. And then another similar type of application in terms of large area substrates is hexagonal boron nitride. This capability exists in 2 forms. One, direct growth using ammonia borane as a precursor, a single source precursor. It decomposes, and you can do this at fairly low temperatures on various substrates and then do a high temperature ceramic conversion. The advantage of this is it gives you a very low roughness substrate for deposition of other types of 2D materials. And we wanted to make sure Joan Redwing was very interested in having this be available as a material that could be supplied to use in conjunction with other types of growth or deposition or transfer processes. Also, you can grow this by direct deposition on copper substrates and then do a transfer just like you would with CVD graphene. So this capability exists, and if there's any interest in substrates based on these materials, they could be provided through the 2DCC. Finally, the last thing I just wanted to put in terms of equipment, there's a high temperature Czochralski system that's available from Thermal Technology. It's been used for a variety of different applications. Again, the key takeaway here, very high temperature capability. You can translate vacuum or various atmospheres, so you can set up and synthesize materials at high temperatures using this capability. In support of all this, we're putting together some support capabilities, namely 3 things. Quartz sealing station is going to be upgraded, turbo pumped for high vacuum capability, rapid pumping of up to 2-inch diameter quartz ampules for sealing for growth or annealing. There's also going to be an ampule loading station. It's going to be part of the 2DCC that would allow for incorporation of various transport agents during this loading process, and then a compounding furnace so that materials could be synthesized outside of the Bridgman system and compounded there and then go into the Bridgman process for growth. Part of what I see as really an important part of the bulk growth capability or effort here is to try and figure out how to really improve the impurity, reduce the impurity levels in the crystals we're growing. And often what you need to do there is go to coated ampules, either pyrolytic graphite, carbon, high purity carbon, boron nitride, materials that are barrier coatings on your ampule to avoid incorporation of materials from the quartz ampules themselves. And this system will be configured to allow for investigation of a variety of different types of barrier coatings on ampules. The timeline for all of this equipment coming online is shown in the next slide. Without getting into too much detail, the Bridgman system was ordered, expected to arrive within the next month. The first CVT system was ordered, is expected to arrive any day now. These two systems will come online with the expectation that Bridgman Furnace would be available approximately May for research studies. The CVT furnace approximately April. And so today, part of the purpose of this presentation is to make everyone aware of this capability and get you thinking about possible research programs. So we expect in about a month to release a solicitation for bulk research topics to coincide with this set of equipment coming online and being available for internal as well as external users to the 2DCC. I mentioned in a previous slide that there's a potential interest in fabricating substrates for other growth. And I just wanted to highlight this capability set that exists in terms of making substrates. Often a lot goes into making a high-quality substrate for subsequent epitaxial growth. And we have all the capabilities here at Penn State for slicing using single-wire, multi-wire, IDOD saws, X-ray orientation to control the orientation of substrates, chemomechanical polishing, dicing, and full metrology to be able to produce a high-quality substrate for subsequent growth. And this is an area that I think is of great interest. If there's ideas or needs for certain substrates for different programs, we feel that we've got the capability not only to grow the material, which is only part of the need, but to actually make it into a useful substrate for subsequent research programs. So, kind of in terms of where we're at with the materials, the initial focus on transition metal dichalcogenides has been structured to, first of all, establish a baseline synthesis capability for CVT transported binary TMDs. And the materials shown there would be the first ones on the list that we'll be synthesizing as this material comes online. And we hope to rapidly expand the range of materials to look at alloys and dopants of these materials. Again, the focus here is to look at samples with unique compositions, unique doping for both internal and external research. And I just want to make the point, this isn't really intended to produce standard materials that you can get through other sources. We're really looking for materials with unique properties that you can't get through standard sources and where there's a strong tie to other components of the 2DCC to try and really link all these efforts together and build some synergy. Part of this then we'll be developing standard characterization protocols for each of these samples. Any samples that are provided will come with a characterization data set, characterizing the relevant properties. And so this is a work in progress to define what these are, but we really would like to have this as a complete capability to deliver samples and really tailor the samples to the unique needs. From a longer term perspective, really one of the goals is to look at comparing the properties of bulk and thin film TMDs, try to understand the impact of the growth conditions, thermodynamics, kinetics on the material properties. Anything that can be understood in terms of pushing the scientific front forward by comparison of these materials that are grown in a well-defined, well-controlled manner with well-defined properties from the bulk side, we think will enhance the ability of the film growth capability. And then beyond that, looking at investigating properties of new alloys and dope crystals. And looking at other applications, a couple examples here, phase change materials and ferromagnetic doping materials. So this is where we see this going longer term, kind of in the probably 2-year and out time frame. The other area that we've started work on, topological insulators, from the short-term perspective, again, using this as a means to stand up the Bridgman capability for these materials, starting with bismuth selenide, bismuth telluride related alloys, and dopants. A couple of figures here to show this, pictures to show this work. These are examples of different vertical Bridgman ampules that were prepared with different selenium concentrations for bismuth selenide, bismuth telluride. We've developed a process in the vertical furnace, vertical Bridgman furnace, established the right types of gradients under different conditions for the growth, have grown a variety of self-seated boules, and then are in the process now of just starting to characterize the first materials out of this process. This slide shows, again, from the seeding perspective, a cross-section where we've got essentially a single grain material. This is about a 5 millimeter diameter boule with a small secondary grain. And then from that, we've exfoliated sections of the boule. We are now in the process then of taking this material and starting to look at electrical characterization of that. That's where we hope to begin that work now, and then move forward to looking at compositional variations and doping variations. And again, these are standard materials or commonly studied materials. We're also very interested in looking at other novel topological insulating materials going forward. But this capability is all up and running right now, and I think we would be well positioned to entertain any kind of research proposals in this area. Looking ahead longer term, new topological materials, semi-metals, topological crystalline insulators are on the list of things that we hope to explore going forward, and then again trying to establish collaborations in terms of the research proposals to expand this effort. But these are areas that we see this capability being directly applicable in the longer term. So I hope that gave you kind of a 30,000-foot high-level view of what we're trying to do from the bulk growth perspective. I just want to point out that there is currently a request for information out there on the website. I think the date for asking for responses is March 3rd. And what we're just trying to do, again, is get an understanding of materials of interest, research objectives, any particulars about the types of materials or needs that you would have from a bulk growth perspective. We're trying to use this information to formulate, then, the call for proposals. It's a very simple form. What this information is shown here. Again, anything you can provide in terms of details about the materials of interest, any kind of unique research objectives or connectivity to other parts of the 2DCC, any information you can provide in these areas would be greatly appreciated. The plan going forward, then, is to release a bulk crystal call for proposals. Expected release date, March 17th. Expected due date, May 12th. We have a couple of months to get back with a proposal. This will use the standard proposal submission portal on the 2DCC website. And in this case, we're really only looking for research project proposals. The requirements are very simple. Information on the PI, a short 3-page project description, and then bio information. This will then go out for external review, come back through some decisions, get selected by the leadership team in terms of prioritization, allocation of resources, and then hopefully pretty quickly get started on these projects. A key point I want to emphasize here is we are strongly encouraging everyone who's thinking about submitting a proposal under the bulk growth effort to please contact one of the key people, individuals, prior to submission to discuss your needs, make sure that the submission is consistent with the capabilities and resources that are available to 2DCC. We really want to get a dialogue going as early as possible to make sure that your proposal comes in with the right type of information and it's going to be able to be approved and supported by the 2DCC. We feel that the key to do that is just talk to us. So the contact information for the key individuals is listed here. Feel free to contact any of us. If you want to discuss your ideas, discuss your proposal, hopefully we can help you refine it before you submit it. And it's not required, but it's strongly encouraged. So, again, to wrap up, I hope I've given you at least a high-level view of the equipment, the processes, the capabilities, and some of the materials of interest in the short term and looking a little further out. Bulk growth does provide the opportunity to investigate equilibrium growth of alloys and node crystals, provide materials for exfoliation studies, and explore new phases, new compositions of 2D materials. So we think this is really a useful connection to the 2DCC. We're establishing a bulk growth facility, emphasis on chemical vapor transport and vertical bridgman growth, and structuring this to have the capacity and capability to grow a wide range of unique materials, compositions, and doping levels. Again, in addition, we're hoping to be able to provide tailored substrates for film growth, and again, trying to really leverage the advantages of having an active substrate in a device or structure or experiment versus just passive devices. So some of these materials where we can provide substrates that meet those requirements is an extremely interesting area. we are really trying hard to tie the bulk growth to theory and characterization as well, just given the nature of this type of work. And then, again, just to reiterate, the RFI is going to be used to formulate a bulk crystal growth call for proposals, which we expect to release March 17th. With that, I thank you and be glad to entertain any questions anyone may have.
Well, thank you, Dave. So this is Kevin. We're looking online here to see if there are any questions, and we do have a question that was asked about in the middle of the presentation. How do you ensure stoichiometry in TMD crystal growth? And the question was directed at both Bridgman and CVT. So I assume the question is related to, are they different in those two different processes? And you answer about the stoichiometry.
Well, with the Bridgman growth, for example, we can control the stoichiometry of the raw materials that are loaded into the furnace and compounded. And often you want to use an excess of one component because if there's an incorporation issue, particularly in this case with selenium, the selenium overpressure essentially by the excess affects the point defects in the material. Once you've grown the material, you can then characterize the stoichiometry to ensure that it's the right crystal phase that you're looking for. So controlling the amount of material that you load into this process modifies or impacts the growth quality of the growth itself. That's how that's typically done in vertical Bridgman. And in CVT, you can do a similar thing by controlling the amount of material that's loaded into the system by using excess components. So it's not uncommon to use excess materials during growth to impact the properties. And another variant of that is actually to do post-growth annealing of a material to try and modify the point defect structure. So I think all of those methods are able to be used to control the growth condition and then follow up with a characterization of the material itself.
All right, any more questions online? While we might be receiving some questions, I just wanted to make a point of clarification about this RFI and solicitation. So the 2DCC is open to proposals at any time for any of its capabilities, whether it be in thin films or bulk crystal growth or theory. But the reason we do these targeted calls is because, the nature of the community is that people need a deadline. And so while it is open to submit at any time, we use these as opportunities to create a deadline for the community to submit proposals. So you don't have to participate in a competition, so to speak. It is open. Any questions in the room here?
So I was wondering if you could explain a bit about the standard characterization you plan to do for these bulk materials and how it's different than what is done for thin films.
Well, I think it obviously will depend on the material itself. For example, for the topological insulators, we're going through X-ray orientation of the boules because of the nature of the seeding growth. Raman for structural characterization, X-ray for structural characterization, and then doing temperature-dependent measurements of resistivity and transport. So that's kind of a standard set for used for bulk growth for these materials. Again, it would depend on the nature of the application for the CVT materials of interest, but we would try and define, and this is, I guess, part of working with the user community, what the specific requirements are for these materials. Again, in this case, what we're tending to do with many of these materials is just make them available in a form for exfoliation, in which case the characterization would essentially be similar to what you're doing for sungrowth.
Anyone else in the room? We got one more here.
So for the Chalcogenides furnace that you have, I'm not really familiar with the technique. Could you comment at all on how it's different from the Bridgman method and some of the other techniques that are available?
Sure. Chalcogenides method is historically used for silicon, oxide crystals like YAG, sapphire. Typically you have a melt, dip a seed crystal in it, rotate it, and extract from the melt. So for that particular process, it's designed, the equipment was designed for that application. However, you have a translation phase and induction furnace. You could actually operated in terms of a Bridgman furnace by translating through that zone. But with the Chalcogenides growth, it's typically a melt growth process where you're extracting the crystal from the melt versus a Bridgman process where you've got a liquid that you're translating through a temperature gradient to directionally solidify it. I think that's the fundamental difference of the two.
Got another question here?
Will there be any facilities for exfoliations and the capabilities for users to come into once they these crystals are synthesized? Are there setups for that?
I believe we have an answer here from Tom Maluk, so hold on a second.
So I don't know if we'll have facilities per se in the 2DCC for exfoliation, but we have a lot of expertise in chemical exfoliation in my group, and we're happy to coach anybody on that. But probably that would have to be done by us coaching you and you doing it, or in collaboration, rather than a user facility set up in the center.
We also have Ron Redwing, who's working in a 2DCC.
Actually, this is an area that we've identified. One of the reasons we've nitrogen glove box is because there are some materials that are very sensitive to the atmosphere. So part of that effort is to start the idea of trying to standardize and bringing the various techniques together and doing the tutorials and et cetera, and bringing users here as needed. So that is an identified area.
Any other questions online or here in the site? So I'd ask that you join us next time as well. So next time is going to be March 30th, and it's going to be noon to 1 again. But that talk is going to be on MBE growth under Roman Engel-Herbert. So please join us then. But let's also thank Dave again for his presentation today.